to the first keynote presentation for Design 2022. I am John Clarkson, one of the program chairs for this conference. Before I introduce our speaker, can I just ask that you write down any questions that you might have during the keynote using the chat function. And this will be the only option you have to share comments or to pose questions to our speaker. So the first keynote, AI, machine learning, robotics, trends, challenges, and opportunities. Our speaker is Professor Danica Kragic from the School of Computer Science and Communication at the Royal Institute of Technology in Stockholm, the same institution in which she received her PhD in computer science, following her first degree in mechanical engineering in Croatia. She's also director of the Center for Autonomous Systems, with research interests in the area of robotics, computer vision, and machine learning. Danica has received multiple awards in Sweden and internationally. So Danica, welcome, and we look forward to hearing what you have to say on AI, machine learning, and robotics.
Thank you so much, John, and thank you, organizers, for inviting me. And for the next 30 minutes, I will be presenting our work that is in the intersection of robotics, artificial intelligence, and machine learning. So to set up the stage and show you a little bit visually what we do, here are a couple of videos of our recent research. We use physical systems, robots that are equipped with various types of sensing modalities, cameras, laser, sonar, tactile feedback, force torque feedback, and equip robots with the help of AI and machine learning methods with abilities to physically interact with the world. Now, some of the application areas have to do with rather classical industrial assembly or interaction in environments which are not yet, but are soon to be completely automated, where jobs such as, for example, emptying and filling shelves is currently done by humans. Now, we are not doing this because we are interested necessarily in automating those works or those businesses, but because they do pose very interesting scientific challenges. And the rest of the talk is going to be very much about what are the techniques we use and how do we push science forward by addressing some of these problems. Something that we are very much interested in is also automating some of the core daily things we humans do, and we do this swiftly without thinking. So we engaged recently in equipping robots with the ability to interact with clothing items, performing tasks such as, for example, folding, unfolding clothes, and trying to understand how we would need to build robots for the future domestic applications. So if there is a robot at home, potentially cleaning, again, ironing, folding clothing, and so on, what would be the perceptual capabilities these robots would need, but also how these robots should move, interact with human, what type of natural interaction robots should have, and so on. Other types of applications, as I already mentioned, have to do with physical interaction. And why is this important? Well, if we think about robots, then in hospitals, for example, or having robots helping on construction sites, there will be lots of behaviors or actions we need robots to do together with humans. Now, direct physical interaction with the human is rather difficult and advanced tasks, and we humans use both the body language, we use language, we use gestures, and other ways of interacting through, for example, compliance, force torque feedback, and so on, to show and instruct the human collaborator what we are able to do, how much weight we are able to carry, and so on. Now, again, some of these examples serve as the inspiration, but also these are far from being solved methodologically from the perspective of control, human-robot interaction, signal processing, computer vision, and so on. Some of the future applications that we foresee, but that are currently rather difficult to address, are various types of teacher-learner scenarios where the information might be to both through natural language interaction, convey what the human, in this case, potentially needs help with if the human is using robot as a tool to get help with extra ingredient and so on. But imagine a scenario where the robot is the teacher and the human is learning how to, for example, bake bread. And the robot, through various types of sensory feedback, vision, for example, observes the dough, understands how the viscosity should affect the appearance of the dough, and instructs humans by saying, well, I think you need more flour, you need more of this and that ingredient, and so on. Now, this would be fantastic. It's just that some of the challenges regarding both modeling the dough, observing its current state, is something that, well, it's difficult mathematically, but also from the perspective of perception. Today, it's extremely difficult to say, just from camera images, to what extent the fingers that are engaging in this rather dexterous activity are covered with flour or with a dough. A part of our research also has to do with understanding human and human social interaction better. Robots can be then used as a tool to engage in various types of activities with humans, and then we can use devices such as EEG to, in very let's say, in detail design scenarios, so for example, game playing and so on, understand what the human expectation or perception of robots' behavior is. We studied this together with neuroscientists and look both into healthy individuals, individuals with diagnosis and so on, so that we can understand how, again, the robots should behave so that humans that are not robotic scientists or not used to use robots or interact with this, they don't get scared, and that they have enough of the training time in order to entrain and understand how my individual's action affects robot behavior and vice versa. Now, if I'm thinking back a little bit about how and what would be some of the keywords in our research, I chose some of the latest work that is cited here, but put in red some of the works that then define the methodologies and the applications these are used in the context of. We use reinforcement learning and addressing some of the difficult tasks of in-hand object manipulation. We study collaborative robots with the help of understanding human activity. We rely on various types of optimization techniques in order to be able to do that in real time and store lots of knowledge in form of some form of an experience that the robot can access, but at the same way use various types of machine learning techniques to adapt this and learn incrementally with the help of deep learning and sim-to-real transfer. Now, when it comes to the application areas, apart from interacting with deformable objects such as clothing, we also look into physical interaction with soft objects such as food and let's say fruits and vegetables. And all of that is then used both in terms practically and theoretically for building various types of predictive models that we study either from the control theoretic point of view or from a machine learning point of view. So for those interested in more detail our work, these are some of the relevant references. My own work, more focused for the past, I would say, 10 years on physical interaction with the world. And these are just some of the examples that inspire me. Our daily interaction with objects using various types of tools, putting our hands and manipulating objects in various types of media. And we do many of these things without, well, what we think, without lots of mental effort. We have done these many times. We have acquired them through our own development. And we also have a tendency of doing these things rather differently. Do we reflect over that? Well, sometimes we do. Now, the expectation when it comes to robotics for the future is that robots will also, as we humans, be able to extract and learn how to do these things solely through observation. Now, observation, just visually, without really trying and understanding to what extent my body is capable to do very dexterous task of, for example, buttoning a shirt or tying a shoe or changing somebody's diaper. Well, you can't really know until you do it. Another thing that I think is very important to be said, that we humans do not have the ability to convey the information that robots need in order to be able to learn how to actually execute this. We can't really say what is the exact force or the torque we use and apply to a knife when shredding a carrot. We can't say to what extent we adapt or change the force or torque when we interact with a plate while just putting it in a shelf when it's dry or when it's covered with oil or with water. So the bottom line here is that the physical properties of the world, such as friction, forces, and so on, change through interaction. And also the properties of these objects. So how do we represent the state of the carrot when in the start or before shredding, when it's a single object, and after the shredding? Is that still the same object or do we call it something else? How do we also define states of objects that are reversible or irreversible? So for example, again, the shredding will put a carrot to irreversible state, while some other objects or interactions we have with the world will not do the same. Now, robots need to be controlled in, let's say, metric coordinates. So they will need those newtons, they will need those millimeters that humans are actually not able to communicate. Of course, visually observing and reconstructing the world, building advanced simulators in order to be able to generate the data for training machine learning algorithms is a viable solution, and one of the ways we address some of these problems. Now, why interaction tasks? Well, I find them interesting from the control theoretic point of view, machine learning, perception, but also human-robot interaction perspective in order to, well, can we understand forces from just studying video information? The majority of our manipulation tasks are contact-rich tasks, and if we are to deploy robots close to or instead of humans for some activities, those dirty, dull, and dangerous jobs, we will need to equip robots with the capabilities of exerting contact-rich tasks. Compared to just movement, contact-rich tasks does need modeling of various types of forces, energy exchange. These are the dynamic stochastic tasks happening in real time. And in many cases, we will need to combine what we call task and motion planning, so high-level and low-level planning, combined with analytic models and data-driven models. We will also need to resort to identifying parameters that are not known beforehand. So if a robot is to manipulate an object that it has never seen before, it will need to understand potentially its properties such as size, whether it's a soft or a rigid object, what potentially is the material the object is made of, in order to understand better the friction coefficients and so on. Now, to what extent is this doable today? Well, there are many things we can demonstrate with the appropriate level of sensing with dexterous robots and so on. So like in this case here, the robot can use its fingers, move them around, apply more force when the weight of the object changes. So it can intelligently understand that the cup has become heavier, and by squeezing the fingers, applying larger force, or re-grasping the cup, it can continue to secure the grasp, the safe grasp of the object. It can also react to external forces as a human would, and demonstrate that, well, some intelligence that we have in our physical body is actually possible to be done through careful, again, consideration of controlled theoretic approaches for doing this. The robot can also, through very simple instructions, learn how to throw a ball, and this is also something humans do through training. So we test many times. We build some memory in our muscles. We use proprioception in a similar way as robots do here. So the robot can learn through carefully designing various types of deep learning architectures through just humans saying yes or no after each trial, learn how to successfully throw a ball on one of the figurines here on the table. And it's using visual feedback here, and it knows where the hand is at all times. So doing this modeling of perception action circles, robots can be equipped with some of the capabilities we humans also acquire by training. Now, why is this relevant? What we really study is the mismatch of these embodiments. So robots' bodies are to some extent inspired by humans, but still, when it comes to number of degrees of freedom, softness, the ways of using compliance, friction, and so on in order to interact with the world, rather different. So one of the scientific questions we ask, what would be ways of using machine learning and artificial intelligence, of building various types of representation, so using representation learning, for understanding what a robot with a certain number of degrees of freedom and hands with maybe 2 or 3 or 4 fingers, what is this robot capable of doing? So if you think of a space of all the actions that a human can perform, can we find a subspace or maybe a different space of potential capabilities, so that we can say, well, while human can do this, the robot can do this, and in collaboration and through designing various types of collaborative tasks, this is what kind of the optimal collaboration strategy may be to achieve various types of goals. Now, we do this again with encoding high-dimensional data. We measure what the human can do with their bodies in interaction with various types of objects. We know something about the kinematics and dynamics of robots. And then we use something like ocean process latent variable models and other types of encoding and representation learning models in order to be able to address particularly this problem. How is this relevant, and for what is this relevant? Well, it is relevant, for example, for prosthetics design and design of future types of robots. So if we know that a robot will be only used in a scenario such as, for example, washing windows or picking or emptying and filling shelves and so on, we don't necessarily need to have a very expensive robot with very many degrees of freedom. We can build robots and robot bodies that are devoted for a specific set of tasks. However, if the robot is to work in a hospital, elderly home, or in our own homes, where we would expect a robot to help somebody to take a shower or help with assistive dressing and so on, we may need a robot that has at least as many degrees of freedom as a human, or potentially even more. How far are we from that? Well, despite the fact that the robot technology is being developed in terms of we have better arms, more compliant arms, more degrees of freedom, one of the area that, again, despite the fact that it has received for the past 50, 60 years lots of attention, is the development of robotic hands. Many of the intelligence when it comes to dexterity and contact-rich interaction with everyday objects sits in our hands. And most of the robots today are still equipped with rather simple hands. Now, when it comes to something like this, potentially assistive dressing and thinking about dual arm system, perception is a big challenge, understanding the state of the clothing item, understanding where the head is, coordinated manipulation and coordination between the two arms and so on, safely putting this over somebody's head, even if that green head would be maybe 4-year-old that is trying to run away from you and so on. So there are many challenges in terms of how do we do this safely and how do we do this in interaction, in more realistic tasks where the interaction is considered to be with maybe elderly people, kids with special needs and so on. Now, in order to be able to systematically then design various types of algorithms and study solutions and compare to also others, we work very much in developing simulated tasks so that we can achieve various types of benchmarking, push the field forward by understanding who has maybe a better way of encoding this rather complex perceptual information, but also design motion planning algorithms that can provide relevant feedback to the robot, so that the robot can perform in real time and so on. One of the recent work from NeurIPS, for example, looked into how we can build environments for studying manipulation of deformable objects. So I'm just going to give you a couple of examples, what is of interest here. So how would we perform motion planning if the robot is to put a tube scarf over mannequin's head, something like I just showed you a couple of slides back, or putting a mask over the ears, putting a backpack with long handles around the mannequin's arms, and so on. And what is interesting here is that we can put some constraints in terms of how these motion trajectories should look like, dependent on whether the human that we are helping can move or has some maybe physical disabilities and so on. So I think that from the perspective of what today simulated environments give us is the ability to systematically test many of the underlying machine learning algorithms that all of us develop. Another interesting aspect when it comes to learning from humans, as I said in the beginning, is just to try to understand what is the limit of extracting geometrical information from 2 or 3D video data. What are various types of, let's say, deep learning networks that allow us to, while tracking the object, also track the full pose of the human hand in interaction with the object. So this is one of the recent works we did in terms of understanding what the human hand does, how the human holds the object, if the human is to pour wine to a glass or just put the wine bottle in the cupboard, or potentially move it from A to B and so on. And these are interesting aspects because then we can use this as an inspiration to equip robots with the capability of using quite similar ways of interaction, or just study what kind of hand would a robot need to have in order to be able to demonstrate rather similar capabilities, and what variety of various types of interaction tasks a robot can demonstrate with 2, 3, or 4 fingered hands. Now, when it comes to the interaction, especially full body interaction, it is not only about being able to track the human, if a robot and a human are collaborating, but it is also very much about anticipating what the human is to do next. Do we humans do that? Yes, we do. We have the ability to extract a lot of information about the physical capabilities of our collaborator. We will change the way we behave or interact with objects we potentially carry together, dependent on whether the human we collaborate with is stronger, taller, or whether there is some prior information that the human we collaborate with has injured left or right arm, and so on. Some of these things can be even extracted from us humans by just observing the way the human potentially non-symmetrically use their body and so on. And I would say that today, despite the fact that robots are really, really good in performing various types of tracking tasks, and we have worked with vision-based tracking for quite some time, it's still very, very difficult to do any long-term future prediction of the human state. Although this is extremely important, again, for designing safe algorithms so that the robot can adapt to predicted or anticipated human activity before it actually happened. And of course, this can happen at different levels, and we can also use multimodal feedback so that the robot asks questions, not just observe visually. But what I would say robotics brings to everything that has been done in computer vision community is the fact that if we consider compliance, so that the human and the robot actually do something physically together, there is also possibility of using wrist-mounted force torque sensors and so on, so that the multimodal information is then used, and better prediction or anticipation can be achieved. However, many of the machine learning algorithms today are still not designed for it's open research question, and this is something that we are addressing, how to use this multimodal, sometimes redundant feedback in order to be able to encode some of these models in the best possible way. What are the representations one can use? We can, of course, rely on skeletons, various types of temporal encoders in order to be able to do this predictive tasks. We can look into many types of examples and use lots of priors in order to be able to anticipate what the human is going to do next. And then we can look also into the quality of these predictions, milliseconds, seconds in the future, and so on. Now, why is this important? Again, it's important because this can then directly be used in designing various types of control algorithms that then can understand better what the human is going to do, and then avoid potential dangerous situations, so that the human and the robot occupy the same space and so on. Now, why do we continue to work with this, and why is it, as I said, an important aspect to have in mind? Apart from the fact that there is a lot of things happening regarding model development, transformer models today, and so on, and that multimodal data can be used. Let me just go to this and give you a couple of examples. I think what is important is that we need to have the ability of anticipating what we call many futures, and be able to track how humans can also through interaction learn what a robot is able to do, and how various types of then deep learning models can be used in an online fashion to provide better and more proper input for safe interaction. I don't have too much time to tell you more about this. I wanted to just let me see if I can do this. Some of the experiments regarding measurement and human, what do we study as scientific problems when it comes to social action, interaction, and anticipation. We look into various types of collaborative tasks where human and robot have a goal of achieving the same goal. And then we try to understand how humans engage in these types of activities and how long the entrainment period is. So to better understand what to focus on in terms of studying various parts of complex tasks, and what we would need to encode in order to build safe entrainment systems. Now, let me leave you with this slide as an inspiration for where I find some of the challenges and open problems scientifically. I think that despite the fact that we have robots that can demonstrate everything from, jumping, rotating in the air, clearing the table, and so on, we still don't have robots that can do everything. And we don't have good ways of also transferring what a robot has learned in context A to context B. So finding task-relevant representations and how to generalize over different contexts, that's going to be one or continue to be one of the open challenges in all three areas that I'm addressing in this talk. We also need to find ways of how to study tasks that generalize over different embodiments. So whether we have robots with 2 arms or 3 arms, or maybe robots with 2 fingers or 3 fingers on each hand, and so on, we need to understand better what subset of actions can be directly transferred, what needs to be still trained in physical interaction with the world, and so on, in order to speed up the development and the learning once robots are deployed in human inhabited environments. More work on multisensory data and basic research in understanding how multisensory data can be used in terms of its redundancy. And then, of course, continuous active incremental learning with minimal supervision. For deploying robots in the real world, we will need to understand better of how to go from rigid to soft and deformable objects, and also how to understand through interaction physical parameters beyond shape. That's why I think that many of the talks that I have seen the titles of today and sessions, some of the sessions I attended, it's very clear to everybody, I think, that we will need to continue to combine the use of analytic and data-driven approaches with various ways of using the priors, and also rely a lot to sim-to-real transfer in order to be able to generate data we need for training some of these rather complex machine learning models all of us are developing. So I'll stop sharing here, and I'll be happy to address any questions out there. Thank you so much.
Danica, thank you very much indeed. And if I could encourage folk out there to put the questions in the chat, please, so we can see them come through. So as we wait for questions, Danica, fascinating talk. Do we learn more from trying to mimic what people do, or by asking robots to find a route to the same outcome?
So a difficult question, and it depends very much, I would say, on the body that the robot has, right? And it's a little bit of a chicken and egg problem, I would say. Do we start with a body and then train that body to do something, or do we try to, from the fact that we have the task, also build the body? But I think what is interesting scientifically is actually maybe use human as an inspiration to design maybe some of these priors. But definitely have robots, if we have the ability to have a robot learn and try, build its own model. Now, I think that the problem is that we have today is that partially robots will find ways of doing something more effectively than humans. But the question is, will humans accept that solution as, as acceptable? Now, thinking a little bit about playing games and everything that we have seen, finding strategies that are better than kind of like humans historically relied on. But it might be so that robots find a better way of using their body, even if that body is rather similar to human. I can't answer the evolutionary kind of minimizing the energy and so on question, because this is what we humans do. But some people, do it more effectively than others, and I suppose that will also be the case with robots.
That's great, thank you. So I've got a question here from James. Fascinated by the talk, and you can see the question there on the screen. Wondering if we perceive working with a robot different to working with a human. Would we accept a robot questioning us, for example?
We do. So from if we just study, the reaction or the EEG data. So when a human engages in playing a game, or a human and a robot, there is definitely a difference. Now, there will be a difference, both in the motor cortex and the visual cortex. We have also done the studies where the human wasn't aware whether it was a robot and a human on the other side, then the differences are smaller and so on. So there are many studies to be still done. And then we also see that difference diminishes the more often the human interacts with the robot, right? Because we do adapt. Now, will we accept a robot questioning us? I will kind of try to understand this from very many different perspectives, the question. I think that sometimes it might be easier to get a question from a robot and being pointed to and being corrected by a robot than by a human. I think that in the human-human interaction, there are so many emotional aspects, shame, the interaction, whether somebody is a teacher or a learner, junior, senior. Many of those aspects disappear when the one correcting you does not have an age, or you don't know how smart or intelligent that thing is, and so on. So I think it might be so that we get hurt or less emotional when getting a feedback from a robot.
So what point, Danica, do you think we'll be learning from the robots and change what we do? Do you see that with your team in the experiments at all?
Sorry, that what aspect?
Well, we think of the robots learning from us.
Yeah.
At what point do the tables turn that the robots do things maybe better than we do? We learn from them.
I think that the interesting scientific question is, how do we learn together? So can we somehow, show that me and my daughter in interaction, or me, my daughter, and a robot have a different way of both conveying the knowledge, storing the knowledge, maybe just through a different type of interaction, think of things in a different ways. And this is how I would like to see it. It's a kind of like an alternative point of thinking of things, right? because when we the more we know each other, the more we assume that with minimal kind of interaction, we just understand each other. So we don't even need to convey words, right? We are just using body language. But I think having a mediator in a way, or a person that doesn't know us or doesn't completely understand us, and asking for clarification, it may also make the communication between two individuals who understand each other, force us to communicate better. So I see it more as a way of enriching even the interaction between humans, rather than, tipping or learning. It's learning differently, but it's, we will need to see how to design all the experiments, I suppose, in order to be able to say, is it better? Is it more efficient? Does it affect how the brain develops? Many interesting questions there.
Plenty of work to do. So there's a question here from Mario.
Mm-hmm.
How long will it be until we see robots in such roles outside of the labs?
Well, it depends on what level of roles, we or the complexity. I think that 25 years ago, there have been first robots put in as museum guides, interacting with humans, being able to avoid humans and things like that. Now we see robots on streets. We are seeing, let's say, more and more robots in malls and so on. I think that the biggest challenge for us is this physical interaction, right? The ability to engage in very complex, high dynamic tasks where you just can't rely that the camera will give you information of where the human you collaborate with is. And our body, we have the skin. It's the organ that covers the whole body, and we can feel contact everywhere. And we still don't have robots that can do that or do it differently. So one of the biggest challenges is that as soon as a human sees something that looks almost like a human, we have a human expectation on it. So we do not even try to behave differently. We treat a robot as we would another human. And that's a challenge. We can't do that. So I would say that apart from the fact that we will at some point be able, maybe, 5 to 10 years, able to see even more complex robots and some physical interaction, we will need lots of entrainment in terms of this physical interaction between humans and the robots, so not to have these expectations on the systems that just look like us, but are very different from us.
That's really helpful. And maybe to pick up on that, there's a question from Ross talking about robots working with the older generation, and whether that brings particular challenges of acceptance.
It's a complex question. So you're asking somebody that has a kid with special needs who is 14 and can't speak and does not have a way of communicating what he wants and needs and so on. And I think that putting that in perspective, so having systems that can really help 24/7. If you are a mom or a daughter of somebody that actually needs that help and you can't provide it, you have a tendency of, hoping it will be tomorrow. I think that I can only relate to mobile phones. First we thought like, why would I need a mobile phone? But then when you get used to it, when it becomes kind of a necessity, you have a tendency of accepting it more. There are extreme questions regarding or problems regarding integrity, safety, and so on that we will somehow need to address. But I think that we will just find a way, because as soon as we understand what this very, I would say, complex systems can do for us, I think that then we will maybe also think differently about the acceptance.
Thank you. Danica, you've spent a lot of time increasingly modeling how humans behave.
Mm.
What would you then advise designers in terms of sort of mainstream product design? What insights have you gained by studying how we move and how we do things that might reflect in just mainstream design, for example?
Now, what I think we all will continue to need as we get older, as we need to kind of have better support and better use of our body. I think that this is like, what I'm very much thinking about. How can we integrate technology and design in order to have the possibility of use our body even more intelligently in all the environments we are in. And what I would really like to see is a bigger mix, so that the products that we use, the objects around us, are actually mediating and helping us to interact better with people with disabilities, right? And that I don't think that we are not yet there, right? And that I would like to see.
Thank you very much. And so just one last question from Mark here. And I like the tail end of the question. What would a killer app be that would start to bring robots more into the mainstream?
Changing diapers. Anybody? Sorry for saying that, but I think it is such a challenge of manipulating something that is so fragile, such as diaper, with something else that is very fragile, such as baby, and doing that safely. If we ever come there, I don't know. There are many humans that can't do that. Some claiming, like my husband, that they can't do it. No, I'm kidding. But anyway, so I think it's that something that is very close to human physical interaction, but also something that has to do with interaction with very fragile objects.
Robots changing diapers, that we must see. I look forward to that. Danica, thank you so much for your presentation today. It's been inspiration to learn of your world, fascinating world, and of its direct practical implications to the world we inhabit in design too. So thank you again. Really appreciate you taking time out to speak to us. Thank you.
Thank you. Bye-bye.